well, fluids don't maintain their own shape. They always assume a shape of a container in which they are stored. Well, I mean, in space, actually, you can have fluid, yeah, because the sun is fluid, for example. Jupiter is also fluid, and they, due to gravitational interaction, they will assume a spherical shape. So actually, if a fluid is free, and if interaction is strong, it will form a droplet. A falling droplet of rain actually is also not contained, but it is also spherical, a sphere. There is a misconception that it has the shape of a tear. It doesn't, and the proof for it is that the rainbow would have a completely different shape if they were like that. So rainbow proves that the droplets of water in floating in air are spheres. Now, fluids have a certain very important property which actually makes them applicable to in the particular situations. Fluids practically cannot sustain shearing stresses. You cannot shear fluid, particularly if a fluid is in equilibrium. If fluid is in motion, there is a certain interaction inside which is kind of similar to a shearing stress, but it is relatively weak, and it is referred to as viscosity. Sometimes people also call it internal friction. So when one layer of fluid moves with respect to another layer of fluid, it will grab that. I mean, they will interact with each other. Now, well, I wanted now to give you a puzzle, something from kind of common knowledge. But you know that when you run when you drive a car, you need to make sure that you have oil in the engine. What for and why? Well, obviously we know what for, right? Because it is to lubricate the engine. Now, how come that oil lubricates the engine? Why don't we? Because I mean, it is that the purpose of this oil is to produce a thin film between the piston and the cylinder, and somehow it lubricates. Why couldn't we cover cylinder with a thin aluminum foil, for example, or Teflon foil, and use the Teflon foil or aluminum foil to lubricate the engine? Why do we have to make that film from oil? Talk to each other now. How come that oil lubricates the engine? So how about if I make drawing here? It's exaggerated drawing, but I mean there is a slit. There is a space between the piston and the cylinder, and this space over here is filled up in a normally operating engine. It is filled up with oil. So here we have thin film of oil. Why couldn't we use here aluminum foil or Teflon? You have an idea? Okay, let's try.
Is it because the cylinder and the pistons change shape and you need the fluid to change shape?
Actually, I don't agree that they change the shape that much. I mean, why would they change shape? Because of expansion. Well, that foil could expand too then. Yeah, I mean, when it gets warmer, I mean, we didn't talk about expansion, but indeed when it gets warm, it can, it does, but this is not the reason. And besides, then because my next question will be, why don't we use water to lubricate engine? Anybody else has an idea? And actually, I gave you a hint. I just, at the very beginning, I described properties of fluids. And one of those properties is makes lubrication possible. Say it loud, right?
That it doesn't have a shear.
There is no, fluid cannot sustain shearing force, I mean shearing stress, right? Because now, let's say that piston is moving up. If piston is moving up, well, it is going to shear that film over here. If it were Teflon, it would react. It would, Hooke's law would create, will result in a shearing stress in that Teflon, and it would be pulling the piston down. I mean, really, instead of Teflon, I could just use nothing and leave piston rubbing against the cylinder. But then, both in the piston and in the cylinder, we would create shearing stresses which would slow down the operation of the engine. Now, if we fill it up with liquid, that liquid now takes care of the vertical force exerted on the cylinder by the fluid. It cannot exert that force. Why don't we use water? Oh, well, one thing is that correct. One thing is that it would evaporate, but another thing is that it's not viscous, but what you really mean is it does not wet the wall, right? This is what you were thinking, because actually we want a fluid which has low viscosity. So considering viscosity, water would be better than oil. Because oil will makes the two surfaces stick more than water. However, with water would be problem to create the film. All right, let's take a look at some other consequences of of interactions in fluid, and particularly I want to turn your attention at fluid on Earth, because for the engineering purposes, most of the time we will deal with fluids in our environment, so we cannot avoid gravity. Stress in a fluid is going, stress in the fluid is going to behave in a particular way. So let's say that I have a cylinder and fill it up with fluid, and on top of it I can even push that fluid from the top. So let's say that this is a fluid which is enclosed in that cylinder, and I'm pushing with a particular force on that piston, which squeezes the fluid and creates stress throughout the fluid. However, that stress is not going to be uniform. Well, because now let's say I'm interested, what is the pressure? What is the stress at this level? I already said pressure, and which pressure actually should I think of? I should think about hydrostatic pressure, yeah, because in fluid we don't have shearing stress, we don't have uniaxial stress, we have hydrostatic stress, and hydrostatic stress is referred to as just pressure. So let's now try to determine what is the value of a pressure at a particular depth of fluid, and on top of it, that fluid is even pushed from the top, which actually happens all the time. If you think about a lake, are we pushing the lake from the top? Well, we are not. Is anything pushing that water in the lake from the top? Yes, what? The atmosphere, correct. The atmosphere is pushing it downward. So even, I mean, what you see over here on this drawing is also applicable to a large container of fluid like a lake. All right. Well, so pressure inside at a particular depth is, well, by definition, it is related to how it is squeezed, and that is, it has to be squeezed from both sides. Remember that stress is created only if a pair of forces is applied. So it is squeezed from top and from bottom. You can think about a infinitesimally thin slice, and and determine now the forces with which it is squeezed. It is squeezed from top and from bottom with forces, with opposite forces, so that slice doesn't accelerate. All right, so let's figure out how strongly it is pushed from the top. We will immediately conclude that from the bottom it is pushed with a force of the same magnitude. Well, so we have to figure out what are the forces exerted on this part of the fluid above the slice, because the slice supports the fluid. Can you see it? All right, so, well, there is a force exerted by the piston, and also that fluid has weight, which means that there is force exerted by the piston, force exerted by the earth, and the third force is exerted by the slice. The force exerted by the slice is opposite to the other two and makes it to behave like it does. And how does it behave now? If it is in this container, how does it behave? In other words, I'm asking, how does it move? It doesn't move, right? It doesn't move. So relate now those three forces exerted on that fluid. Are they related then? Yes, they are related. They have to be related in such a way that the fluid doesn't move. Yes, the center of mass of that fluid doesn't move. If the center of mass doesn't move, what does it mean? That the sum of the forces exerted are which forces? External forces. Sum of the external forces has to be zero. How many of them do we have here? 3, correct. So sum of those 3 forces has to be 0, which means that the force which is exerted by the slice is opposite to the sum of those 2. If I think about magnitudes, I mean both forces, this force and this force, are exerted in vertical direction. So the magnitude of the sum of those 2 forces is equal to the sum of magnitudes of the 2 forces, right? Do you see that? If the forces, if 2 vectors are in the same direction, then the sum of magnitude of the sum is equal to the sum of magnitudes. Which means that magnitude of the force exerted by the bottom slice is equal to the sum of magnitudes of those 2. And by definition, pressure requires that I divide it now by the area on which that force is exerted. All right. Now, this is force exerted by the cylinder. Force exerted over here. Well, if I think about the cube over there, I see that from the top, that cube is held by the piston. Piston has to exert a force equal to pressure multiplied by the area, or actually the force exerted by the piston divided by the area will correspond to the pressure created at the surface. So pressure at the surface is equal to, force exerted by the piston is therefore equal to the pressure in the fluid at the surface multiplied by the area of that contact surface. Now, in order to find weight, I would, if I multiply, I will have to now divide this entire fluid into slices. And for each slice, well, cross-sectional area times height of the slice gives me the volume of the slice. If I multiply by density of fluid, I will get mass of the fluid, and multiply by acceleration due to gravity, this will give me weight of the slice. And then I add it from throughout the entire depth, so this will give me weight of the of that fluid. And why do I integrate it rather than multiply density of the fluid by volume of that fluid? Because I don't know if that fluid is uniform, correct? Yes, so it could be, and really it is. In principle, it is denser at the bottom than at the top. Particularly if the fluid is gas. I forgot, but I think about over 90% of the atmosphere is below 10 kilometers. I mean, not further away than 10 kilometers from the surface. Although by convention we assume that the thickness of the atmosphere is 100 kilometers. Most of the atmosphere is here, and air at the surface is much denser than air much higher. This is why when we fly passenger planes, we don't fly it at 50,000 feet, but we fly it at 30,000 feet, about 10 kilometers above the ground. It would make sense if we were able to create lift much higher. It would make sense to fly higher. Why? It would be cheaper. Why? Because there is less drag. Correct. The higher we fly, the less drag there is. So less fuel will have to be consumed. Problem is that we don't have lift there either. All right. Well, in many cases, I mean, if we consider fluids like water, which is a pretty common fluid for engineering applications, then it is pretty incompressible. Stress grows really very fast if you strain that fluid. So if you try to squeeze it, the reaction force exerted by the fluid is very strong. So practically you cannot easily change density of water. So even at the bottom of the ocean, density of water is similar to density of water at the surface. So practically water has uniform density. Well, if density is uniform, then we can simplify this expression, yeah, because we can take density in front of the sum, acceleration due to gravity 2, unless this fluid goes into space, and this area over here as well. What did I do? Oh, I divided first everything by A, yeah, because I have A over here, and in that sum, I can take it in front. Now, this integral, if the density is uniform, it's easy to integrate, and the result will be density of the fluid, acceleration due to gravity times depth, which means that in the gravitational field, pressure of fluids depends on the depth, and the deeper, and it's a linear function of depth. The deeper we go, the higher is pressure. Now, where did I use the fact that it is gravitational field, that it is in a gravitational field? Because there was weight. Yeah, I included weight. If this was not in the gravitational field, then I wouldn't have weight over here, and pressure would be determined only by the force with which we squeeze that fluid. So pressure then would be uniform, and everywhere would have the same value. Now, this type of pressure actually can happen also in a situation Well, where you accelerate. So, for example, in a car, when you drive your car and make a left turn, well, then think about that fluid, the air which you have in the car. That air is actually trying to stay on the right-hand side of the car. It is in this non-inertial reference frame, there is a centrifugal force exerted on it, on that air, right? So it is going to be compressed more on the right-hand side than on the left-hand side, which means that what would be the distribution of pressure in the car when you make a left turn? Or on the right-hand side surface of the car, pressure is going to be higher than on the left-hand side. And actually, this would be a very similar formula to that, except that now h is a distance from the left door. If a plane accelerates on a runway, also something like this happens, yeah, because now you have a fluid. I mean that air, which is being accelerated forward. Well, it doesn't, in the non-inertial reference frame of the plane, it is accelerated forward. Well, so where air gets compressed? At the back of the plane. Pressure at the back of the plane becomes higher than pressure in front of the plane. So now if we wanted to use this formula, h would have to relate with the distance from the front of the plane. I mean, in the plane and in the car precisely, it is at the angle because we still have gravity acting as well. So we have a combination of those inertial forces and gravity. It would be more appropriate to think about this when we are in space and accelerate spacecraft or turn spacecraft. All right. So how about if we come back for a moment to a discussion of which we have had yesterday of a dam, and if I think about how to find out force exerted on a dam by water. Yeah, let's say I wanted. We said that the shape of this dam is such so that the shearing stress everywhere, so the shearing stress is uniform. And if I wanted to find out shearing force at this point, well, I will have to figure out what is the force exerted. How about if I actually draw it three-dimensionally? If I wanted now to find out the force exerted on this part of the dam, how would I do it? Well, distribution of pressure along the surface is not uniform. Pressure here is lower than pressure here. So if I consider a tiny fragment, and well, how about if I actually even think about a fragment which is a rectangle like that, so let's say deeper. So let's say that this width is dh, and let's say that the entire dam has width w. How strong is the force exerted on this differential surface? Well, I would need to multiply pressure by the area, right? And so I would write that this dF. So the differential force exerted on the differential strip of the dam is going to be equal to the pressure at that location, right? So let's say that this is at depth h. So I have to put pressure at depth h and multiply it by the area of that fragment. And area of that fragment, it is a rectangle, so it would be width times height. And explicitly now when I write down what is the pressure, so consistently with that formula over there, I would have to write down the pressure at the top plus density times acceleration due to gravity times depth multiplied by width and multiplied by height of that strip. So what would be the force exerted on the entire segment? Well, I would have now to integrate from 0 to h this expression. All right, I'm not going, I mean, it's easy to do next. We set already the integral. We can also actually think about another, because yesterday we were talking only about the shearing stress which is created in the dam. There is also tensile compressive stress, because I could also think about a torque exerted on the top part. If you think about this top part, water exerts a torque. And so if I consider just a point, let's say how about this point over here, the center of it? Well, center of the force is somewhere between these two levels. It is closer actually to the bottom because the forces at the bottom are stronger. Right, so we will have a torque. What would be the direction of the torque? Show me with your hand which will be the direction of the torque. Okay, some people say this way, some people say that way. I'm happy that you recognize the torque is perpendicular to the drawing. It is perpendicular to the drawing. Now the torque exerted by water, well, about this point, the center of the force is somewhere over here. Right, so position of the center of the forces is a vector like this, forces to the right, so using right-hand rule, torque is in. Yeah, so the torque exerted by water is in. Well, how come that it doesn't tip? Correct. Something exerts a torque, an opposite torque, to have it in peace. I mean, it's again the same problem like with this. Now, let's say that this is the dam, and I'm pushing it over here. So it broke. Right? Why it doesn't break over there? How does it happen? Well, we would have to choose a better material than this one. Yes, so the internal interaction is stronger, and that internal interaction results in a torque balancing that external torque, which means that internal torque has to be in this direction, right? Which means that this part of the bottom of the dam is doing what to this side? Pulling it down, correct. And this side is pushing it up with opposite forces. And over here you can drill a hole again. It will not affect. So if you want to make a corridor in the dam, it should be in the center, because that part doesn't do anything. The distribution of the tensile compressive stress is like that. So we have torque toward us, which actually now brought me to another puzzle which I have for you. And obviously you would be able now to calculate this torque. You would have to, why don't you actually do it? Try to calculate how the torque depends on the height, right? So you can find out that lever I mean, if you consider this slice over here, well, center of the force is somewhere there, so this is lever arm now. Do you see that? All right. I wanted to ask you a puzzle now, because now we were considering just a shearing stress, so we saw that the area of the cross-section of the dam were supposed to be a linear function of the depth. How about if I design now 3 dams? Yes, so water is always on the left-hand side. We will have a dam like that, or actually, we can go even further. Dam like that, like that, like that, and like that. 1, 2, 3, 4. Which design would you choose? How about if you have a brief consultation, talk to each other for a moment, which design would you use? And well, I mean, I know that a lot of you will use, because you saw various dams, so you recognize that you have never seen such a shape of a dam. But why? I want you also to find out why we designed them the way we do. Talk to each other now for a moment. Yeah, water is always on the left-hand side. Let me also give you a hint over here. Think about the torque. I mean, the tensile compressive stress which results from the torque. Yeah, what torque internal interaction has to balance? Anybody over here would like to comment? Would you like to comment? Oh, why not? I mean, what was your opinion about it?
I like number 2.
Okay, number 2 is a good solution. Now, is it because you saw dams constructed that way, or is it that you have a good argument? What kind of argument did you came up with?
Well, he thought 3. I would take 3 because I think we'd fall over.
Which way? Oh, well, no, I mean, you could actually make it. I mean, you will just have to put appropriate reinforcement into that. So in engineering, we are able to, I mean, whatever we want actually to do, we could do it. Well, we will just, number 3 indeed would be more expensive than number 2. We would have to give a stronger reinforcement. And why did you think number 3? Actually, number 3 is neat, right? Because the wall is that outside wall is vertical, so it looks nice. But it is more expensive, though. Yeah. So water is on the left-hand side. Why did you choose 2? Oh, because this is you thought that it is correct. I was wrong with number 1. What do you say? Aha! Yes, very good. Problem with number 1 is that when the water level goes down, the dam will fall to the left. I mean, why? Why? Yeah, because I mean, well, say it again. So that.
Because you're reversing your tension and compression force directions. When the water's high, you have a tension force on the inside of the dam. Low, that turns into a compression force from the way the dam that's not being supported by water.
Right. Yeah, because normally water exerts torque in this side, right? So I mean, if we reinforce the dam, which way let's say that it is made from a reinforced concrete. On which side would we have to put the rods? Inside, on the side of water, correct. No matter which design, if water is up, then the rod should be, reinforcement should be on the side of water, because this is where the tensile stress occurs. The other side doesn't need really the rods. Well, however, if the water level drops, then it seems, why actually? I don't see exactly why the torque would reverse, why the internal torque would have to reverse. Well, so why it doesn't drop to 0 and the dam is relaxed? Aha, because we have gravity over here, right? Yeah, do not forget about gravity. So, over here, I mean everywhere, our center of gravity is somewhere there. So now think about which way the gravitational torque is exerted. Over here, gravitational torque is exerted in the opposite direction than the torque exerted by water. So actually, if we were able to maintain the level of water, this would be a good design, because rather than internal reinforcement, gravity could balance that torque. However, we will have to maintain the level of water all the time. Well, over here, indeed, it is that even when water level drops, the gravitational torque is, well, we get torque that way. So it would be good to have some rods on this side, but it is not as drastic as this one. And we can design it in such a way that it will hold. Now that one is a bad design. Why? Because the torque, gravitational torque and torque by water are in the same direction. We have to reinforce them much more. Well, that one is hopeless, right? Both torques are in the other direction, and I mean, internal stress has to take care of gravitational torque and the torque exerted by water cooperating with each other. Now, can anybody here windsurf? Have you tried that? Oh no, sailing is something different. Yeah, because I mean, if you look at I mean, who saw people windsurfing? Most of you. Did you see how they hold their sails? Well, yeah, because I mean, they hold their sails completely differently than on the sailboat. Well, on the sailboat, actually, you are unable to do it. It is always the drag torque. I mean, the force or the lift exerted by the air makes the sail lean away from the wind, right? However, windsurfers lean their, I mean, if the wind is from this side, they will lean the sail on this side. Why? Aha, right, because they take advantage of gravity. So if the sail is leaned this way, let's say wind is from that side, right? So the torque exerted by the wind is which way? Towards you. And gravitational torque is away of you. Actually, if you lean it sufficiently low, the force which you have to apply, because now you are a part of the system. So force exerted by you is an internal force. Now, if you are smart, you will make gravity to fight with the wind. Well, if you are an inexperienced sailor, what you would do is you will lean like that, yeah, and you will fight both gravity and the wind. So holding sail in this at this angle when you windsurf is pretty hard. If you lean it on you and you ask gravity to help you, then it's quite simple. Try windsurfing, it's really good, a lot of fun. All right. Now, another trick which we can use with fluids, well, Pascal has noticed it, and therefore it is raised as a Pascal's principle. Well, if we have certain distribution of pressure, if we change now the force exerted by the piston, if you look at the formula, the previous formula, what will happen? How about if I write that formula? Yes, so pressure at depth h is equal pressure at the surface, which is created by the piston, plus density of the fluid, acceleration due to gravity times depth. If I increase pressure at the surface, see how the pressure throughout the fluid is going to change. Where it is going to change more, at the bottom or at the top? I will, so think about it now. You have certain distribution of pressure with, let's say, 0 force. Now I will push it. How the pressure will increase? Is it going to increase more at the bottom than at the top? It is going to increase more at the top than at the bottom, or equally? Equally, correct. It is going to increase equally. Yeah, because for a particular depth, the pressure is not going to be uniform, so pressures will be different, but the changes in pressure are going to be equal everywhere. Well, if I'm smart, I can use it to such a device, or such a system, which is called hydraulic press. So let's say that I have one piston over here, and of a relatively small area, and another piston with a large area. And, well, in order to increase force over here, obviously the force over here would have to increase as well. Yeah, that fluid is pushing the piston, so I wouldn't be able actually to increase this force if there was nothing holding that piston. So, but you can have a car on this piston now. And well, let's compare the two forces. The force with which I push this piston with the force with which the fluid is pushing on that piston. Well, that force will be equal to pressure of the fluid at this surface multiplied by the area of that surface. On top of it, pressure over here is the same as pressure over there. Yeah, so I divide magnitude of this force by the area of this piston. This gives me pressure here and here. Now that force will require that I multiply pressure by that area. So if I have appropriate ratio of the areas, I can apply much higher force. I mean, the hydraulic press will move much heavier object than I can apply force. Let's say that this area is 100 times greater than this one. So if I apply a force of 2 pounds over here, just 2 pounds, I could easily lift Mark with a force of 2 pounds. Can you see that? Yeah, because if I can, force exerted on this side will be 100 times greater. And this is how hydraulic press works, and it is used in every garage to lift a car. Well, so I think that this will be probably the right place to end the lecture. So see you tomorrow.